going to begin now. It's just about 6:05. Yeah, so my name is Michael Banks. I'm at University of California, Santa Barbara, and our group is doing work with soft robotics and its intersection with Koopman mode analysis. And I should acknowledge my collaborators, David Haggerty, Patrick Curtis, as well as professors Elliot Hawks and Igor Mezic. Yeah, so soft robots have a number of interesting advantages over classical rigid robots. So if you imagine the counterpart to what we have on the right here would just be some finite number of linkages. A soft robot has this huge amount of versatility because it can bend and conform, and you can imagine it, shaping its way through some type of constrained space with obstacles and so on. And our robot on the right here shows just how simple also these are to construct, at least relatively. What you're seeing here is basically a balloon hanging vertically. It has a central pressurized balloon, as well as 3 muscle balloons down the side of it that can control its movement. And you get a much higher strength to weight ratio than you would with some type of steel linkages, because it's really just a balloon and all the strength comes from air being pumped in. The challenges, though, are in the modeling and the control. This is a nonlinear system, and it's effectively infinite dimensional because you need to keep track of the location of the robot down all the way along that continuum. And then also the governing equations are unknown to begin with. So this is the movement that our robot is capable of achieving. Existing soft robot arms emphasize high precision, and they do some amazing things with picking up objects or pointing and that type of thing. But we wanted to focus on high deflection, very much nonlinear and fast and aggressive movement. And so what you can see here are a couple of the positions available to our robot. The first 3 are helical type motions that it can achieve. And then the bottom 3 are very high deflection, where the robot's actually curling over itself, pretty much all the way over. Yeah, so a soft robot system is inherently nonlinear, especially when we move into this large deflection regime. Even worse, the dynamics are unknown, and it would be kind of a nightmare to try and analytically derive the governing equations here. You'd have to measure all sorts of complicated interactions between the materials and so on. So really the natural thing to do is to move on to data-driven methods. And in particular, we favor the Koopman operator-based methods because you really are able to genuinely model some of the nonlinearities in the system. And also, it's highly interpretable. You get all this interesting spectral structure out of it that I'll talk about. So we do have to pay the price of high dimensionality, though. You multiply the number of observables you start with to many, many more, but hopefully you can span some type of subspace, and as you add more observables, you get a better model, and I'll talk about that a little bit more. So start with some arbitrary dynamical system of this form. We're working in discrete time, so you have T, some type of nonlinear transition operator, well, not operator, just a function, acting on your state. It gives you your shifted state, x plus, and the states live on the state space, M. And so that's the typical model of a dynamical system. We want to expand our view of the dynamics onto the space of functions, which we call observables, phi. We can define the Koopman operator, K, acting between, between the space of functions, which gives an evolution of the observables under the dynamics via pointwise composition. So you've moved from a finite dimensional state space to an infinite dimensional function space, but actually you can prove that the Koopman operator is linear no matter how nonlinear your original dynamical system was. So you can't store an infinite dimensional anything on a computer, really. So we want to be able to build a finite dimensional linear approximation of the Koopman operator. There are existing algorithms. The one we choose is dynamic mode decomposition, in particular a few twists on the original DMD. But first, what you have to do is choose a finite set of observables. What you really want is for these observables that you choose to span some invariant subspace of the Koopman operator. And if you can do that, you can essentially model that entire subspace of the Koopman operator. But in principle, those are usually pretty difficult to choose. So first, what we do is we're collecting the XYZ locations of those 15 red motion tracking points you saw in the picture of our robot. And they're located down the length of the robot. And then for each of those measurements, we take 10 time delays of the measurements. And what happens is, as you fill your observables with time delays, there are some theorems that you can prove that show that this does a pretty good job of filling out the invariant subspaces for periodic systems, which is a good enough heuristic for us here. So this, when you use time delays in DMD, it's called Hankel-DMD. Really what we're doing is Hankel-DMD subscript C with control. We're going to get a B matrix, an input matrix out of this as well. But first thing we do is we start with 2 snapshots of data. X would be the unshifted data. Y would be the shifted measurements corresponding to the original unshifted measurements, as well as a matrix of inputs. There are M of these measurements, which are the commanded pressures in those 3 lengthwise muscles. We apply our vector of observables to the data. So this, again, expands the dimensionality of our data. And we formulate the following problem. So really we desire matrices A and B such that we get this nice linear model here. This inspires the following minimization problem, which is really just Frobenius norm minimization of the predictions minus A times the originals and B times the inputs. And the solution to this is given by the Moore-Penrose pseudo-inverse down here, and you can pull apart A and B as you need them. And really this is the foundation of the algorithm, so it's pretty simple. It is just Moore-Penrose pseudo-inverse. And then A and B together approximate part of the Koopman operator, actually. And go to the next slide. Hopefully, yeah. So I wanted to demonstrate what the choice of observables has on this model, or what the effect is. The x-axis for both of these plots is the number of data samples, and you see in both cases the RMS error, which is the y-axis, is decreasing as you increase the number of time samples. But one very popular choice of observables, and it's pretty natural, people think the Taylor series, right, is monomials. But as you can see, as we add monomials, so that blue is just the state, this color red is the state plus the squares of the state, and so on. As we add monomials, we're actually decreasing the predictive power of our model. And this is because as you stray away from the time average, from the neutral position of the robot, the tails of these higher order polynomials really aggressively climb, and so you can get some modeling error there. But on the left, or on the right, sorry, we see that as we add time delays observables, consistently our model gets better. So time delay observables were really nice here. So what is the control problem that we're trying to solve? Well, first of all, the control algorithm we use is really simple. It's the linear quadratic regulator. This is the benefit of using a linear model, of course, and the fact that we can use this for a very nonlinear system is kind of remarkable. And so what we're doing is we are specifying this red reference point. So the robot starts at the initial purple, which is neutral, hanging down. The LQR controller, in this case, is very aggressive, and very briefly we jump up to this orange transient state. And then after a while, we settle down to this final state, which is reasonably close to the reference state. And I have a video that demonstrates this, so you can actually see it in action. And one thing I want to point out is that all of our control so far is done completely in open loop over this long time horizon. So as we transition to a closed loop model, we think this will be even better. So the next thing I want to show before I show my video is what do we get from the Koopman operator formalism besides just a linear model? Well, linear models give us spectra, right? And so even for this nonlinear system, we can start to talk about its spectrum, and we can get the essential modes, frequencies, growth and decay rates, and eigenfunctions. So the usual eigendecomposition of this A matrix gives the Koopman eigenvalues and Koopman modes, V, which should be pretty familiar, but the eigenfunctions are defined to satisfy the following. And really, this is just the very familiar eigendecomposition, but K is an operator, phi is a function this time. And in order to compute these, first of all, you need to compute the eigenvectors of the conjugate transpose of A, which are W, and then you do the following complex inner product. And these are important because each eigenfunction spans its own invariant subspace. So really, if you can find these are the most natural possible coordinates you might want to use to study whatever dynamical system you're studying. You can get a lot of physical information out of that. And then here's what the Koopman eigenvalues look like, or at least the most significant ones for our system. And as you can see, they're all dissipative with some oscillatory components, as you might expect from our robot. And I'm scaling each of these bubbles by their respective Koopman eigenfunction evaluated at a particular state. And the highlighted green ones correspond to modes which are large but also not purely decaying, and I'm going to show what the modes actually look like in action in the video. I'm going to show right now. Yep, so title slide. Okay, here's our robot in action. So first of all, you want lots of basically random training data, right? You want to expose your robot to as many possible states and configurations as possible. And so this is us running through kind of the almost quasi-static type of dynamics of the robot. Now we move on to the much more aggressive stuff. So when we apply step inputs to the robot, we have very aggressive transient dynamics as well as settling dynamics onto some new equilibrium position. So these are the two types of training we used to build our model, and all of this data is collected. I think it's at least a half an hour total of data. And then on the top two slides, you can see what the actual motion capture points look like. The bottom two plots here are the pressures in those three muscles. Okay, what do the modes actually look like? And I might want to stop it here. So on the upper left, this is that eigenvalue plot I showed. And then we have these three pairs of modes. So mode pair 1 here is shown here. And 1 minute left. I'll just let these play. You can start to look through the different modes of your system and pick out physics, right? So for example, on the left, these are the three largest modes, which correspond to the time average plus 2 complex conjugate modes, which give you this simple oscillation. And then I need to show the actual control. So with way too few modes, you get poor agreement, and then with enough modes, you get good agreement. And the rest of this video is just a demonstration of a bunch of control positions that we are able to achieve. And since I'm over time, I will just allow questions right now because that's it. So